Hello, everyone. Welcome to another episode of Q&A about history of science and technology. So people have been telling me that they would like to consume some of this content in slightly smaller bites. And so I'm going to try and make my answers to questions somewhat self-contained so they can be chopped up and provided in future. That will make little difference, but I'm just letting people know that in case it seems weird. All right, let's see. We have a whole bunch of questions that have come in. I was wondering from RBS, asking about the history of automata theory and its applications until today. All right, so, the word automata is surprisingly old. You might think it was a modern kind of computeristic word, but it's not. I think it was out and about even in the 1600s. And I think people, as soon as people kind of had the idea of clockwork, they had the idea of making kind of clockwork-like toys, whether it's music boxes or whether it's more elaborate kinds of things. Sometimes they had it associated with clocks. In fact, they would have, the cuckoo clock where the little bird comes out and pecks for a while and then goes back in or whatever else. Those were called automata, and they were various kinds of devices that had basically gearing-based structures inside, and where there were typically actions that would take place. There would be the duck that walks with its feet and, nods its head and opens and closes its beak, and those would happen at different rates, and those would be determined by gearings, and that was sort of a common form of automata. And people, I think even Descartes in the 1600s was talking about automata and the question of, for example, philosophically, whether we are like automata, whether we are like, the duck toy with its gearing and so on that operates in a completely deterministic, mechanistic way, whether there's something more to, for example, human existence than something mechanistic like that. So this notion of automata was definitely out and about in the time of philosophers in the 1600s, 1700s, things like this. Now, and there was a famous, actually specifically a duck, I think it was in the 1800s, that was famous for having sort of realistic features of a duck, including it could eat, it could do all kinds of things. And it was merely an automaton in that sense. And I think of course, there were also fake automata like the Mechanical Turk that was supposedly an automaton for playing chess, but which actually had a small person inside the box, so to speak. It's sort of interesting that the Mechanical Turk could have been a thing for decades, because it meant that people's understanding of what was conceivable from a kind of clockwork automaton was really pretty off. That people didn't understand that chess was a level of thing that was not achievable by an automaton like that. So anyway, that was kind of the history. Now, I think that there are, by the time we get to the 20th century, there are kind of more elaborate derivatives of automata, like the idea of robots that came from this Czech playwright, right, which turned into like these movies like Rossum's Universal Robots and so on. It was the 1920s era movie, I think, that included kind of automata-like robot creatures, humanoid automata that were up to all kinds of things that made the movie interesting, I'm sure. I don't know whether I've ever seen this movie. I've certainly heard of it, though. But so that was kind of in the early part of the 20th century. Again, this idea of the robotic now, as opposed to automaton kind of thing that was going to be built with a mechanism and act like an animal, person, whatever else, that was a thing. Okay, well, now we get to the more formal use of the term automaton and the idea of finite automata. So I think the way that kind of emerged was this. So electrical machines had been a thing starting in the late 1800s. There were an increasing amount of sort of electrical machinery that had electric motors. Faraday, for example, but once there was electromagnetic induction, you could start having electric motors. Those became practical, and you ended up having these electromechanical switching systems where you would open and close a switch, and that would allow electric current to flow or not. That would switch on a motor. The motor could actuate things. You could get all kinds of elaborate stuff that was operating with a switched electricity. And so I think the early thing that happened was increasingly complex kind of electromechanical devices, including things like electromechanical calculators, but electromechanical elevators, electromechanical machines in factories, things like this, where sort of the main idea was to have some kind of switching network that would be kind of where this switch would turn on, that switch would turn off, and you would have some essentially logic implemented in the switching network. And I think the early kind of way of thinking about automata in the more formal computational sense came out of the sort of electrical engineering of things like that, of, is the elevator, does it have its doors open? Okay, that's one sort of state of the automaton. Does it have its doors closed? Is it going up? Is it doing this? Is it doing that? So I think that was sort of a thing that became increasingly kind of a design methodology in electrical engineering, was something where one was thinking about states of the finite automaton, states of the switching system. Now, I think in, let's see, there were several lines of development that will have come together. So the notion of so that's a very practical kind of automaton with electronics and switches and moving parts and so on. A quite different kind of thing that is equivalent to an automaton is something that comes out of pure mathematics, and specifically out of algebra, where you're constructing things like monoids. Okay, so a little bit of history there. Back in the notion of, people had understood numbers and integers since antiquity, but the big advance of the 1400s and so on was the idea of algebra, and the idea that you could have symbolic variables, x and y and so on, standing for numbers, and that you could do manipulations merely at the x and y level that will be true for all numbers. But still, the x's and y's were supposed to actually stand for numbers. The sort of big idea of the 1830s, and particularly people like Évariste Galois, was the idea that you could have things that weren't, where these variables didn't stand for numbers. So for example, one of the alternatives would be that the variables stood for operations like do a rotation by 30 degrees, do a reflection, and that you could have essentially products of those things, do a rotation, do a reflection, do another rotation, etc., that you could represent those just like you can represent an algebraic expression, x times y times z times w or whatever. You could have something where the x always represented a rotation by 30 degrees, the y always represented a reflection, something like that. And you could write down sort of a symbolic expression that represented that series of operations. And then you could have an algebra of such things which say, reflection by this amount, if you do it twice, you'll get back the identity. Or if you do a rotation and then followed by another rotation, you'll get a different thing and so on. So you have these algebraic expressions, but where the variables involved in the algebraic expressions are not things representing numbers, they're just things representing other operations, or representing just abstract, or just being abstractly variables A, B, C, and so on. So that was kind of a key idea in what led to group theory. By the end of the 1800s, there was kind of the notion of universal algebra, which was, you just put in these symbols and there's a multiplication operation, and the multiplication operation is just a sort of symbolic thing. We don't necessarily say what the multiplication operation actually does. It just has certain relations that say, A times B is the same, where times is this generalized multiplication is the same as B times A or something. So that led to a bunch of questions about a bunch of sort of ways to construct a generalized algebra. And in the period in the last couple of decades of the 1800s, where there was this big push to kind of formalize and generalize mathematics, this was kind of one of the directions, was to think about mathematics as kind of, it's all at some level universal algebra. And I think that led to a sort of a yet different version of finite automata, because essentially what happens there is you are thinking in your automaton, you are saying, okay, I'll, so now let's talk a little bit about the more abstract version of automata. Maybe I should say something about what automata turn into. Let's see. Gosh, okay, so slightly technical point. So you've got this automaton, and the way that one thinks about it is it's in a certain state. Then it makes a transition to some other state. So for example, the elevator has its doors closed, then it has its doors open, then it's in motion, then it's not in motion. Each one of these things has a transition that goes from a state, like elevator is stationary with its doors closed, elevator is stationary with its doors open, elevator, etc. So you can make a transition, for example, from the state elevator is stationary with its doors closed, elevator is stationary with its doors open. You won't get a transition from elevator has its doors open and then it starts moving. That's a transition you don't want. And so what you end up with is this graph where you have nodes in the graph representing states and edges in the graph representing transitions between states. So, for example, I don't know, you can invent tons of these kinds of finite automata situations where you're kind of representing things that can happen in terms of this kind of graph of nodes and states. Now, an alternative representation is to say, let's just represent the transitions by symbols, and that, one could have one edge as an A, another one as a B, and so on. And then we can write down something which is like this universal algebra idea, where we're essentially describing that graph by giving relations associated with sequences of symbols, because that's a way of saying, oh, AA is the identity. That means if you follow the A edge twice or something, you'll get back to the identity. By the way, it gets very confusing, because for any time when you can represent a symbol as a transition, you can also represent the nodes, the states with symbols, and you can be saying which sequence of states do you go through. That's another way of representing what's going on, and so on. But in any case, so another big sort of use case application area of the finite automaton business was in this area of thinking about symbol sequences from universal algebra defined by certain constraints, which ones could occur, which ones could not occur. That was sort of another branch to the whole thing. Now, there were several sort of pieces of unification that happened. So one piece of unification that happened in the 1930s, I think, yes, was Claude Shannon, his master's thesis, I think it was master's thesis, maybe it was PhD, I'm not sure, at MIT, was something that showed the equivalence between switching circuits, and which are like finite automata, and Boolean algebra, logic. And so this was a sort of an important unification point of these ideas about switching networks, logic, automata. This actually gets quite technical now that I think about it. But okay, so another branch was a guy called Stephen Cleaney, who was one of the early American kind of active people in the area of mathematical logic. And in the 1930s, I think, he invented this thing that's usually called the Cleaney star operation. So, oh boy, the other branch of this whole thing are so-called regular languages and regular expressions. So once you have this notion of a graph where you can go, we have these transitions and you can go from state to state and so on, it's a way of representing kind of possible languages where you could say, I can have the letter A, I can have any number of letter A followed by one letter B. followed by any number of letter C, for example. And that you can represent in terms of a graph where you have a loop that has an A on it, and you keep going around the A loop, and then there's one edge that has the B edge, and that takes you to another node that then has a C loop going from that node. So that's one way to represent things, is in terms of that graph. The alternative, which one is familiar with from using computers and so on, is you can write something like A star, B, C star. And that was a thing that was developed by Kleene in the context of mathematical logic. And it was then taken by operating systems like Unix and the predecessors of Unix, and the text editors like Tico and so on, as a way to represent kind of match this pattern, an A any number of times, a B, a C any number of times. And that was sort of another branch of kind of the use of finite automata for things. I mean, and that, again, that case of what started in algebra became a thing in mathematical logic, became kind of one of the levels in the sort of hierarchy of describing languages, the very lowest level, became a thing when early computer languages were being built for making lexical analyzers for computer languages. Like, okay, you've got that blob of characters and it's supposed to be a number. What can it be in that blob of characters? Oh, it's some number of digits, any number of digits. That could be a number, any number of digits followed by a single decimal point, followed by any number of digits. That can be a number. That you can define all of those kinds of lexical units in terms of finite automata. And that was another big use, was in creating lexical analyzers that could say, this is the blob of stuff that can represent a variable name, this is a blob of stuff that can represent a number, and so on. There's sort of the higher level that goes beyond the sort of regular language lexical level and goes to the level of context-free languages of saying, you've got this thing followed by this thing, followed by this thing, where you have a more tree-structured kind of thing. That's the sort of next level up in the so-called Chomsky hierarchy. But that stuff was coming in the 1950s as kind of early computer languages were starting to be developed and things like that. So that was another branch of the finite automaton world. Yet another branch has to do with deterministic versus non-deterministic finite automata. So one of the issues is you've got this kind of graph that represents your finite automaton. And then one of the uses for that graph is to say, does this finite automaton representing this regular language, does it accept a given sequence of symbols? In other words, is there a path that you can go through in that graph that will consume that sequence of symbols? So it might be A, B, C, and that would be something that was consumable by that finite automaton I described before. But if it was, for example, A, B, C, that would not be consumable by that finite automaton. So you would say that that finite automaton does not accept that sequence. Okay, so one of the issues then is there, when you are when you're sort of going around the finite automaton and you're sort of feeding in some sequence, is there a unique path that you will follow, a unique sort of interpretation as a set of moves in the finite automaton that will correspond to a given string? And that's so-called deterministic finite automaton. But it doesn't have to be that way. It can be the case that a given string has many different interpretations, many different paths that correspond to it in the finite automaton. It can be the case that at every node, so for example, a very simple example of this would be, at a given node, let's say that there was an A in the string you were trying to read. There could be a single edge that goes out from that node that has an A on it. So you know which way you've got to go if you read in an A from the string. On the other hand, that node could have two A edges coming out from it. And in that case, you won't know which edge you have to go out on. Okay, why is this relevant? Well, it's relevant because there's a whole notion of deterministic versus non-deterministic computation. There's computation where you specify the input program, you specify the input to the machine, let's say it's a Turing machine, And there's just one sequence of states that the machine can go through based on that program and that input. But there's also the idea of non-deterministic computation, where there can be many possible sequences of states that the machine can go through. Why is this relevant? There are problems that are, for example, easy to solve non-deterministically, but hard to solve deterministically. Famous example of this is factoring numbers. If you could just non-deterministically, that is, you just try all the paths, you just find a sequence of integers that is, you enumerate all possible sequences of integers, then you can figure out, is one of those sequences the factors of a given number? And but non-deterministically, if you say, I can try all the possibilities, it's easy to say, I'm going to get the winner somewhere. But if you're forced to say, I have to only get the winner immediately, that can be a very hard problem. This is the P versus NP problem, is the question of whether in fact it is true that there are problems that can be solved non-deterministically easily, but where the deterministic solution is necessarily difficult. And that remains an open problem. We can talk about that separately. But so in the general case of an arbitrary computation, there's this question of what can a deterministic Turing machine do that's always following through state after state versus a non-deterministic one that can check out many different paths. This is also a story of the hope for quantum computers, is that they are something which can act sort of like a non-deterministic Turing machine and check out many paths. Again, there's a great complexity in the way that you kind of determine what the answer is, and that's a place where I think some of that tends to fall down. But in any case, most of the time, when you have a deterministic computation and you have this non-deterministic computation for Turing machines, the ultimate things you can compute with deterministic and non-deterministic Turing machines are the same, but the speed with which you may be able to compute them may be vastly different. It may be, for example, exponentially different. Okay, that's a slight sort of side story to the question of finite automata, because it turns out that for finite automata, it was proved in the 1950s that the deterministic and non-deterministic cases are equivalent. So for any, you can always make from a non-deterministic Turing machine, a non-deterministic finite automaton, you can make an equivalent deterministic finite automaton. It might conceivably be exponentially bigger, but in terms of the speed with which you can accept things and so on, it's the same, unlike for things like Turing machines. And so that was a result. Two people I know, Dana Scott and Michael Rabin, were mid-1950s, I guess, had this result about non-deterministic finite automata, and that led to a specific algorithm, which I've implemented several times in my life, for actually turning a non-deterministic Turing finite automaton into a deterministic one. Okay, well, so what? The finite automata, as I say, are used in the lexical analyzers of basically understanding any computer language. That's one of their common uses. I've used finite automata quite a bit because when you have cellular automata, sequences of cells where they get updated in a series of steps, and at each step, you're just changing the color of a cell based on the colors of its neighbors. In a cellular automaton, it turns out that the set of states that you can get to, so let's say you start the cellular automaton off from all possible sequences of black and white cells. Then the question is, as you evolve the cellular automaton, maybe it just turns into all white. So any initial configuration of black and white cells, the black just dies out and it's all white. Okay, but there are more complicated cases where it doesn't evolve to some fixed state, but it evolves to some state that has potential structure in it. But that structure, there's less states that it can evolve to than that you can start from. If you allow yourself to start from all possible states, the set of states you get to is a smaller set. Turns out that set for a one-dimensional cellular automaton is the set that will be accepted by a finite state machine, a finite automaton. So that ends up giving you a bunch of other uses of finite automata, and you can do things like you can assess sort of how complicated is that set. I called it regular language complexity. How complicated is that set you can characterize that by what is the size of the minimum finite automaton that will accept that set. So anyway, a little bit on finite automata. I would say that they are kind of, another thing I should say about finite automata is that most questions you can ask about finite automata, there's a finite answer to them. For example, if you say, I've got two finite automata, are they equivalent? Do they accept the same set of strings? Oh, you can answer that question. Finite automata are very decidable. They don't have questions that have sort of where you can require infinite proofs to do things. As soon as you go above finite automata, as soon as you go to, let's say, well, context-free languages are the next level up on the sort of Chomsky hierarchy that involve sort of trees of where you're specifying clauses and subclauses and so on. Then, for example, the question of whether two context-free languages are equivalent is no longer decidable. And for example, if you go, instead of talking about the one-dimensional case of a finite automaton, where you say, oh, I'm just going to have this string of characters coming out, and I'm going to accept this, I'm going to define with this graph whether I allow that string or don't allow that string, whether that's a valid integer or whatever or not. The one-dimensional case where I've just got that string of things, that's decidable. You can always answer those questions with finite amounts of computational effort. As soon as you go to the two-dimensional case, blows that up completely. As soon as you start saying, oh, I'm going to have this two-dimensional thing where I have these kind of local conditions, like I say, it's like a tiling, where I say I have these local conditions, where I say, I just want these tiles right around where I am and so on, then it is no longer the case that you can answer these questions finitely. It becomes a thing where there are all sorts of undecidable questions and so on. So finite automata show up as sort of a base case that is that's very manageable, so to speak. They also, the thing I didn't really go into in detail is the correspondence between finite automata and Boolean algebra and logic. That's another whole branch of things, which was again part of the story of the Shannon switching theory as equivalent to Boolean algebra thing from, I think, the 1930s. Okay, a bit of a long answer to that question, a bit more technical than I expected. Let's see. It's a question here from Zayden. How did scientists figure out the source of the cosmic microwave radiation? Well, let's see. Let me try and tell a bit of that story. So people have been wondering forever and ever, where did the universe come from? How did the universe start? And there were all sorts of theories. I mean, for example, there was, well, in many kind of cultural traditions, there's this notion of kind of eternal return. The universe is a cyclic thing. The universe has, people didn't know how old the universe was. People didn't know how old the Earth was. But the question that people generally tended to believe that the universe had either always been around, maybe it was changing, but it would return to where it had been, and so on. The big kind of how did the universe work type moment probably came when Einstein was figuring out general relativity, the theory of gravity in 1915, where the original kind of equations that he wrote down had this very awkward feature that they would imply that the universe expanded. And so Einstein said, but of course the universe doesn't expand. So let me add a term to the equation, the so-called cosmological term, to basically prevent the universe from expanding. It's kind of like the universe would be, it's kind of like an additional kind of mass everywhere in the universe that will kind of pull the universe back from expanding. Okay, so that sort of seemed like a good idea at the time in 1915, but by the 1920s, Edwin Hubble had discovered that the universe actually was expanding by looking in a telescope and seeing that there was a Doppler shift in the spectra of distant galaxies and so on. And that there was a relationship between the brightness of something and its and how much it was moving away as measured by its Doppler shift. So then it became clear, okay, the universe was expanding. All right, so what did that mean? What were the possible things which would cause the universe to expand? There were really two primary theories, the so-called steady state theory and the so-called Big Bang theory. And the Big Bang theory was originally named as kind of a mocking of that idea, because people were like, that's a crazy idea that the universe just started in a kind of a big lump and then started expanding. A much more plausible idea seemed to be that somehow new matter was coming into existence in different places in the universe, and that's why the universe was expanding. And so a number of astronomers in the 1940s and 50s who were big, I think Tommy Gold, Fred Hoyle, they were the big people in the steady state theory. And George Gamow was one of the people on the Big Bang side of things. And so people had kind of imagined maybe there could have been the universe could have started really small and hot and expanded, and there was some idea that if that happened, that there would be relic radiation left over from the time when the universe had been really hot at the beginning. In the steady state theory, there was no such relic radiation because the universe had always been kind of big. It had never been sort of scrunched down into a small thing that was very, very hot. So, okay. So then the next sort of part of the story was communication satellites. So Sputnik was launched in 1957. Sputnik was supposedly launched for International Geophysical Year, right? It was launched as a way to, it's one of its cover stories was it was launched as a way to map out the gravitational field of the Earth by seeing where the orbit would go and map out, where there are sort of, when you have similarly mapping for the moon, for example, the gravitational field of the moon shows the moon has a great big lump on one side, the Earth doesn't. But in any case, there was, I would say, more a geopolitical, technological show-off than really to do with the International Geophysical Year. But after 1957, there were satellites in orbit. By, when was it? 1960, I think. Bell Labs had already put up, I think it was called Echo 1, was the first kind of communications satellite that was this giant balloon made of mylar where you would bounce a radio signal off it. And then subsequently there were other communication satellites that people were putting up that were that had actual radio receivers, radio transmitters, and they were actual repeaters effectively. Okay, so then the next thing was, okay, we want to make these radio antennas that are going to communicate with satellites. And let's see, there's another piece to the story, which was a chap called Jansky, Carl Jansky, in the maybe 1940s, 50s perhaps, 40s, I think, who had discovered that there was intense radio emission from some places in space, particularly the center of the galaxy, Sagittarius A, if I remember right. That was a thing where there was essentially radio noise coming from space. And that was the beginning of radio astronomy. So that's another piece on the side. Okay, but people were making radio transmitters, and they particularly wanted radio transmitters, radio receivers that would communicate with satellites in the microwave band, not quite in the same radio band, I think, as the radio telescopes were operating in. But so at Bell Labs, 1964 or so, there were these guys, Arno Penzias and a chap called Wilson, I don't know his first name, who were tasked with, make better radio transmitters, receivers to communicate with the satellites. So they did that. And the problem was they just couldn't get this receiver to, they thought they had this very good receiver with very good characteristics and so on, but it always seemed to have some noise in it. And so the question was, what was that noise? And they realized the noise was coming from all over space. And there had been previously the radio astronomy stuff, there was noise coming from a particular direction, which was the center of the galaxy. But most, there were other places where it was kind of much quieter in the radio spectrum. But what these guys found was that actually there was a small amount of sort of residual noise at an effective temperature around 2.7 kelvins that was coming from all directions. What was that? It actually didn't take very long for people to say, that's probably something associated with the early universe. Oh, maybe the Big Bang theory of the early universe is right. And in the 1960s, there was kind of a duking out of these two theories. And I think what really kind of probably tipped things over, in addition to the cosmic microwave background, I don't think there was a huge amount of controversy about what the cosmic microwave background was. I mean, people might have imagined it was just random emissions in the galaxy and things, but I think it was pretty clear by the time it's in all directions that that can't be a viable thing. But I think what really sort of clinched things was when it started to become clear that you could actually understand how chemical elements were produced, how helium was produced in the early universe, and that you could predict things like the fact that in the universe there's a quarter of as much helium as there is hydrogen, and that you could actually do a computation that would deduce that. That was one of the easier ones. That deuterium is actually a rather hard computation, and that was much more sensitive. And I don't think it was until the 70s, 80s, that got well worked out. But it was sort of a thing where people understood, oh, in the first second of the existence of the universe, we can use nuclear physics to start working out these nuclear things. And a person called Willie Fowler, who I knew, who was much involved in that working out of the sort of early nucleosynthesis and so on. And it was kind of a big exercise in nuclear physics. And I think that helped kind of convince people about this. So that's I believe the story of cosmic microwave background. As I say, it was as a case where the theory came before the observation, and then when the observation occurred, it was kind of like, oh, it fits that theory and not that other theory. Subsequently, there were other things that were observed, like the fact that that there's sort of an interesting thing that the Earth is moving at about 1,000th of the speed of light relative to the cosmic microwave background. So you thought it was the same in all directions. It's actually not. It is defined by the center of mass of the universe, what the rest frame of the cosmic microwave background is. And it's kind of weird that we now observe that we're moving relative to the cosmic microwave background, because one of the big things that people had said, in 1900, that had led to relativity theory, for example, was this idea there is no preferred reference frame in the universe. It had been the case. People had thought that when it came to the transmission of light, that light was transmitted through space in the same kind of way that sound was transmitted through the air, that sound is compression waves in the air, and it requires there to be air there to transmit sound. And so there was this idea of the luminiferous ether, the light-carrying ether, that will be the analogous thing for light. And interestingly enough, even when the equations of electromagnetism were written down by James Clerk Maxwell in the 1860s and 1870s, he absolutely believed in the luminiferous ether. He wrote down his equations. He thought his equations were describing the dynamics of the luminiferous ether. Turns out the equations were right. The luminiferous ether was not right. And what was done in 1900, Michelson and Morley did this experiment looking as the Earth goes around its orbit. Is there an ether drift? Is the speed at which light goes affected by by which way the Earth is going, where the Earth is in its orbit relative to the luminiferous ether, assuming the luminiferous ether is at rest? Well, so what they discovered is, oh, there is no ether drift. And so that's what led to this kind of the speed of light is the same in all reference frames thing, which is what led to relativity. Unfortunately, you go another 80 years later or something, and people discover that the cosmic microwave background is actually not isotropic. There is a preferred reference frame. It's the rest frame of the universe. It's the center of mass of the universe, and we are moving relative to it. So the fact that the Michelson-Morley experiment was done in the way it was done, with the precision it was done at, was something that led to the idea of relativity. But in fact, if it had been done in a different way, it would have led to a different conclusion. Oh, actually, there is a preferred reference frame. Relativity is still true, but the justification, the kind of philosophical justification for it isn't quite the same. It is interesting, the times when there are theories that get developed where the framework, the sort of understanding of the world is completely wrong, but the theory is still correct. One that I've been looking at recently is the theory of thermodynamics, where Sadi Carnot was operating in the 1820s on a completely wrong theory of what heat is. He thought heat was a substance, a fluid that kind of suffused different materials, not that heat is the result of molecules bouncing around. And he developed these ideas about Carnot efficiency and things like this on the basis of this completely wrong theory of heat. And in the 1850s, people then sort of fixed the idea of the theory of heat, but it turns out what Carnot had deduced in the 1820s was still perfectly correct, even with this different interpretation of how heat works. So it's sort of interesting when that happens, and that's something that happened in the case of the cosmic microwave background. Anyway, that's that story. Boy, okay, here's a question, much more techie question. Questions from Aaron, and it's asking, why didn't containers become more popular until Docker around 2013? Seems like they would have been useful very long before that. What did people do instead? You know, one of the things that's always shocking about the computer industry is that every quotes new idea has been seen before in some other form. So I have to say, when you've got a big blob of software and you want to take that big blob of software and have it run on another computer, how do you do it? Well, back in the day, you would do it by putting that software on floppy disks, taking the floppy disks to another computer, reading the floppy disks into that other computer. Now, obviously, it didn't, then when computer networking became common, you could just copy the file from one computer to another, except, whoops, most pieces of software weren't just one file. I mean, even Mathematica, now Wolfram language, I forget when it was that it crossed the point of having 10,000 files. And it was, in the very early days, most programs were just a single binary. But then people realized, and whatever data that binary needed, if it needed a dictionary, oh, it was just some data that was part of the binary. But then people realized it was much more convenient if you factor things out and you have, there's the binary, and then you have various resource files that are separated from the binary, whether it's the setup of the menus, whether it's the artwork for the startup screen. Those things don't have to be in the binary. Back in the earliest days, those things were always sort of in the binary as one big blob of file. But so I would say by, actually probably wasn't, well, let's see, when did all that stuff come in? I would say in Unix in the late 70s started to be a place where, I don't know, something like the Unix spell check function would use a file in the user dict directory or some such other thing that was a separate file that wasn't just burnt into the binary. It was something that had been factored out. So I think that type of idea of sort of factoring out resources is something that became pretty commonplace, well, certainly by the early 80s. So that meant that when you said, I'm going to send you the program, it was more complicated because you had to send not just the single file that was the executable thing that the operating system would start running, but all of the dependencies that were in there. The other thing that happened was the idea of libraries. So back certainly by 1980, even in the late 70s, it was possible to have a running program, an executable, and then link in other executables while that executable was running. So it's like the computer is running, it's got its program counter, it's like, oh, I'm executing this piece of code here. Oh, the next piece of code I execute, oh, came in from this other file here, but it's now read into the memory of the computer, and that's what I'm going to execute next. So this idea that you could link in external libraries began to be a thing even by the late 70s. It began to be a thing even in early Unix systems. It was a little bit scary, and you could crash the machine and all kinds of other things, still can in some cases. But that was a thing that sort of gradually advanced, the notion of libraries and then dynamic libraries and so on. Dynamic libraries weren't really a thing until sometime in the 90s, which was, again, a place where instead of just saying, there's this one binary, there's this one executable, here it is, go run it, you would be like, well, there's this one executable, but it's going to call dynamic libraries, which come from files, and they'll have to be read in, and so on and so on and so on. But anyway, so the basic point is, by probably the late 80s, it was really commonplace to have a software distribution that wasn't just, oh, here's this one file, but a big collection of things. You know, I'm thinking my first big software system, SNP, was also that was from 1979. That also had lots and lots of files in it. So it was, and the question was sort of, how would you install that object? And on Unix, for example, or on VAX VMS, or one of the other operating systems that was sort of a modern-ish sort of large computer operating system, essentially what you would do is you would like send the program on a tape, and then somebody would read in the tape, and they usually use the Unix utility tar, for example, or the analogous thing on other operating systems. And it would take what was on the tape, and then it would unpack it into a collection of files. Those files would sit on your computer system. Then you'd have an executable, you run that executable. On personal computers, it wasn't as easy as that. There weren't things like tar utilities that would unpack files. It was all a little bit more complicated. And in addition, when operating systems that had GUIs started coming in, there were all kinds of registrations that you had to put into those operating systems. You had to say, oh, when you have files which have a such and such ending, I want them to be opened by this program automatically. Oh, when I have this thing, I want it to insert itself in the menu system in this way. So it became the case that it wasn't just a question of, oh, put the files on the file system. It was more like knit yourself into the operating system. So that led to the whole world of installers. And so, for example, when we first built Mathematica, 1988, it had installers, and actually we built those installers. And we built installers for all the different operating systems that existed at that time. And it was a whole bizarre technology of installers. And then there started to be companies that sprung up. And it was like the first time I heard of a company whose sole business was making installers, I was like, oh my gosh, what is the world coming to? This seems like a crazy thing. But that got more and more and more complicated as programs started to have thousands and thousands of files, and there started to be all this kind of registration stuff that you had to do and all this kind of thing. And so that led to, first of all, the sort of more and more complex installer mechanisms. And then it's like, well, how do we actually package all this stuff up and just stick it on a computer and have it run? And it's even much more complicated when you are dealing with something like a thing that's going to be a cloud system, for example, and you're doing something where you are setting up a server that's got all kinds of tentacles. It's got to say, how does it connect to the internet? What's its domain name? How does it do, how does it deal with user authentication? How does it do this or that thing? And there's sort of the ball of wax gets bigger and bigger and more complicated. And so it's sort of the fact that got so complicated is what led to the desire to have some kind of standardized technology like containers that would allow you to take this sort of complicated octopus with all these tentacles flapping around that were connecting to all these different parts of the operating system and so on, and package it all up. Now, at different times, different things became containerizable in different ways. I mean, still, databases are not heavily containerizable, and that's usually a thing that sort of hangs off to the side. It's now in terms of the details of why Docker took off, I think there was a certain sort of coolness factor to the whole thing, and it's a typical Silicon Valley type story, and I don't know the full details of that one from the inside, so to speak. I just know it as a sort of consumer of those things. I think there were several technologies that were kind of vying at the beginning, and then there was sort of free ones and non-free ones and different business models and so on. I think it also was a thing that, as Amazon, AWS, and other cloud services, cloud service providers sort of came online, it was convenient to have this idea that you would have sort of a thing that was packaged up that you could run on those cloud services. But then, of course, in the usual dynamics of competition in the computer industry, then somebody said, "Oh no, let's have an open version that has that's more is a standard." And usually that's a reason. That's because some underdog basically is saying, there's some company that has kind of that sort of owns this market. Let's make a sort of an open thing that will kind of allow us to get into that market without having to say, "Oh, we're making another competing thing, but we've got the open one that is going to sort of be transportable to everybody." And I think there was a certain dynamic of that happened in the world of containerization. So that a few comments about containers. Oh yeah, actually, there's a comment from J3 reminding me of something. Yeah, this is a right, good point. Okay, J3 is reminding me about virtualization. Yeah, I should talk about virtualization. That's another interesting can of worms. So, the whole idea of computers that can run software is you have one universal computer and you feed in different programs, and then the computer can do different things. That was the idea that eventually launched the whole computer industry. That idea came out of mathematical logic, came out of the idea of Turing machines from the 1930s and so on. Although the route by which that theoretical idea sort of connected with the practicalities of making electronic calculating machines that would be universal in the sense that you could feed them any calculation to do, that was a slightly circuitous route that brought those things together. But by the 1940s, late 1940s, early 1950s, that was kind of a thing. The universal computer was a thing. And so then in principle, given any computer, you can make it do any computational operation. But in practice, different computers have different built-in instructions. So the actual code you need to run on one computer is different from the code you need to run on another computer. And so that meant that for a long time, you would have, "Oh, I've got the software. Oh, it exists for a PC. Oh, it's completely different software that exists on a Mac. Oh, it's completely different software that exists on a Linux machine," for example. And for example, when we were first bringing out Wolfram Language Mathematica in 1988, there was a giant zoo of machines that existed at that time. There was a lot of the personal computers were like the IBM PC and then the Mac. That was kind of a big part of that space. There were companies like Atari and Commodore and so on, which also were in the personal computer space. And then there was a big collection of companies in the workstation computer space, Sun, Apollo, HP, and so on. And then there was another collection of companies in the kind of supercomputer, et cetera, companies like Convex and Ardent and Stellar and so on, a lot of different companies. Every one of those computers had an incompatible incompatible instruction set. So every one of those computers needed a different binary to be created. So like in the case of Mathematica Wolfram Language, the original core code of the system was written in an extension of C that we developed because it was at a time before C++ had native compilers and so on. So we developed our own kind of object-oriented extension of C. Then progressively over time, more and more of Wolfram Language is written in the language itself. So it matters much less what the base sort of core language is. But back in those days, it was basically a giant lump of C code, millions of lines of C code, and we had to port from one computer to another. And that was always a big adventure. How did you port from one computer to another? I think probably the most spectacular porting story was, what was it, a Cray 2, I think. It was a supercomputer. We finally get the thing up and running. It was a big, a lot of effort to get it there. And we type in the first sort of computation, 2 + 2. And I kid you not, it gives back the answer 5. And it's like, how could that possibly happen? And the answer is because on that machine, it was so oriented towards numerical computation that it stored every number as a floating point number, basically. Floating point numbers were really its fundamental way of dealing with numbers. And so integers were kind of a sort of a hack relative, at least the integers we wanted to deal with were kind of a hack relative to that. And this was somehow some weird interaction between the representation of numbers and the fact that this was an integer, which led to 2 + 2 = 5. But it's kind of sort of a strange thing there. But in any case, back in those days, there was probably 50 different binaries that we had to support on all those different machines with all kinds of separate testing on every kind of machine. Okay, so then one of the things that became sort of an idea was, well, let's have a virtualization layer where you can say, well, we're actually running a such and such machine, but we will virtualize another machine. And a universal computer says you can always do that. That's kind of the proof that a universal computer can work is, oh, that universal computer can compute the same things as that other universal computer, because the first universal computer can just run a program that emulates the second universal computer. And so that was a theoretical proof known since the time of Alan Turing in 1936, that was possible. But as a practical matter, it's like, you can't be serious. You're not going to be able to actually emulate. I mean, I remember people talking about this in the mid 80s. Would you be able to emulate one kind of computer on another kind of computer? And then people slowly started saying, well, we can emulate the instruction set, but the instruction sets were quite complicated. And then it was like, well, okay, we can emulate the instruction set, but what about the operating system? What about the system calls? Oh, that's a whole nother can of worms, and so on. And so, but there was sort of an increasing interest in virtualization and an increasing interest in basically being able to take a single piece of hardware and essentially run multiple virtual environments on that piece of hardware. And I'm trying to remember when I first saw that really working. Even when we built, let me think. That was the thing that was super useful as the cloud services like AWS came online. And certainly when we built Wolfram Alpha and launched it in 2009, the pure virtualization technology was okay. Virtualization of databases was not a thing. And I'm trying to remember all of the details, but that was certainly a time when the virtualization was something that had happened. And the point about having a virtual machine is that then you've got sort of your whole machine, it's all encapsulated. And if you're worrying about computer security, oh, it's just the it's all, there's an enclosed kind of machine within a machine. I'm trying to remember, because I at various times I've been interested in what's the overhead associated with virtualizing like that. And the common case of virtualizing, which wasn't obvious at the beginning why it will be useful, is virtualizing a machine of one type on a machine of the same type, as opposed to virtualizing, having a Linux running on your Windows machine or some such other thing. It's a different kind of, it's the same idea. And then there are operating systems like the Mac operating system, which has never been is not set up to be virtualized. But yes, I think that was, I'm now trying to remember, because I certainly lived through a bunch of this history of working out, what is the virtualization overhead? Do we really want to run virtual machines? Is that really a convenient thing to do? Oh, the other thing I should explain is one of the advantages of virtual machines is that you can kind of, at a moment's notice, you can kind of bring up a new virtual machine. You've got one piece of hardware and it's like, oh, I need to be running, 20 web servers on this piece of hardware. Oh yeah, okay, great. Now I need to be able to run 22 of them. I just start up 2 more virtual machines. And you have a kind of a seed version of the virtual machine, and you just instantiate that version of the virtual machine and it starts running again. Of course, it's a complicated story. I mean, there's again a story that comes from things like forking in the operating system. So one of the things which, when I first, encountered Unix back in 1978, I was like, what on earth is this fork operation? Why would I want to take a running program and make a copy of the running and basically make it so that I can have another version of that running program that sort of starts from exactly the same place as the first program, but then, you know, progressively separates off. Why would I ever want that? And it took me a little while to understand kind of what was the great value in having that possibility as a way to set up processes and operating system and so on. And it's sort of a big generalization of that idea is this kind of, well, let's set up a whole virtual machine and let's take this virtual machine image and let's just instantiate, hydrate this sort of freeze-dried virtual machine and let it run. And I guess that I'm trying to remember the whole entanglement of that with, I mean, I think the Docker story is more of an installer type story than it is a story of, but I think these things are all very entangled because, you know, by the time you have a virtual machine, you've got to have sort of a version of what's in the virtual machine, and you've got to have, and then you've got to have, you know, where do all the pieces of the virtual machine connect to and so on. Anyway, that's a few thoughts on that. But oh yeah, there's a comment from J3 here about mirroring machines. Yeah, that's another. Oh boy, yeah, the computer technology is complicated. I mean, that's another whole issue is, oh, you know, I want to set up 100 machines for people around my company or whatever, you know, and I want them all to be the same. How do I make 100 copies? And there were specific pieces of software that did that. You know, sometimes that gets very complicated because there are application programs that run on those machines that are locked to a particular machine and so on. There's a whole other history that we could tell about the history of copy protection. I think somebody asked about that another time, which again is one of the features of all of this containerization. And oh, well, when you bring up the container and it has software that cares about the fact that you can't clone it, you know, how does that how does that reactivation of the software work and so on? All right, I think I'm running out of time and I have to go to my day job here. Let me see if there's anything I can just address quickly here. You guys definitely give me my memory a run for its money. I think that I have absolutely never thought about the history of containers and virtualization and so on. And to kind of unpack that is a little challenging. I will say that I do remember back in, this must have been the early 90s, people who were making, friends of mine who were making kind of microprocessor innovation. One of the things that they were hoping for was that they would sort of have an instruction set and microprocessors that could sort of routinely emulate all other microprocessors. That became less important as Intel, for example, started dominating and the x86 architecture started sort of dominating the world. And now it's again more important as ARM architectures are sort of out and about and they have to emulate x86s, and it's all gotten more complicated again. And somehow the whole process of, you know, oh, it got simpler and then it got more complicated again, it all kind of repeats. And just like we were, you know, for a while, it was like, oh, you know, you just take the C program and it will run on any computer. Well, yeah, no, not really. Now it's like, oh, you've got this website, it'll run on any browser. Well, not really. And so, you know, a lot of these things that were like, you know, everything kind of standardizes down to something and then it radiates out again and it gets complicated again. Oh yes, William is remembering that Apple had a Motorola-to-PPC emulator for their PowerPC Macs. Yeah, I think we were part of the original demo of that Apple had of, look, you can really make a port of raw software from one computer to another. And that was sort of a big dramatic moment. I think Theo Gray from our company was the sort of on-stage personality with Steve Jobs sort of demoing, yes, we really managed to make this port. And it really was made in a couple of days because Apple, with its secrecy and so on, was like, you know, the people who were actually working on it were like, come to the secret room in Cupertino or wherever to prep this right before the announcement of the whole thing. So it really was done in that period of time. I think the thing that always surprised me with these emulators was, is the emulator good enough? Let me give you an example of where, I roll my eyes a bit because, the history of the computer industry comes again and again and again, around and around and around. WebAssembly is yet another story of, emulating emulators and so on. I mean, that's a story of, can you write in JavaScript something which will run, random C code, for example? Can you take compiled code and run it, in this crazy tower where there's sort of JavaScript interpreter in the browser that is really running assembly code? And now maybe you can cheat and run the assembly code directly in the browser, but you don't want to do that because of computer security concerns in the browser and so on. And so I remember maybe 10 years ago now, a little bit more, we had to make a decision. Building out our cloud system, we had built for 20 years. We'd built the user interface for our whole notebook interface system. That was very lovely and is very lovely and is very smooth and so on, running directly on operating systems and GUIs on computers. And then the question was, okay, we're going to get this stuff to all run in web browsers in the cloud. How are we going to do that? Well, people said, look, there's this WebAssembly thing, and it's emulating any, you can just take a binary and run it in WebAssembly. And it's like, well, let's see whether that really works. And of course, there were tentacles hanging out. So for example, I remember fonts were an example. Fonts are often very deeply connected to operating systems. That was a tentacle that was hanging out. And it's still not the case that we could take a binary that represents some of our sophisticated notebook user interface technology and just put it in WebAssembly and have it run. WebAssembly has other uses, but that's not something even a decade later that's really going to work. And this is always a challenge in sort of the computer industry. And this is a reason why it's worth knowing some history. It's like, what's going to work, what's not going to work. I'm sort of always reminded of a very early thing in the workstation computer space of the sort of two bets that were taken by different companies, by Sun and by Apollo. So everybody knew that on these workstation computers, there was going to be an operating system and there was going to be a Windows system. And the question was, which was underneath? Was it the operating system underneath, like a Unix operating system or something, on top of which was built a Windows system? Or was it the Windows system underneath, on top of which was an operating system that managed files and processes and so on? And Sun bet on, operating system underneath, Windows system on top. There was a certain amount of cruddiness to do with some of the way that got implemented, but that was the thing they did. Apollo betted on it being on the other way around. And the problem was that turns out the other way around wasn't a good idea, because the Windows system was just a much more complicated piece of software than the operating system and much less well developed. And so the operating system was, it could have bugs and it could cause the computer to crash, but it had been pretty well shaken out by the time that it was being used on this, the Unix was being used on this computer. And so it was a much more stable thing to say operating system underneath, Windows system, which would be much flakier and would crash much more often. But if the Windows system crashed, well, you'd be thrown out into the operating system and at least all was not lost. But if you had the operating system on top, the Windows system underneath, the Windows system, goes crazy and crashes, and boom, your computer has crashed. So it was sort of interesting which one of those was a bet worth taking. And I think, one might have been able to work out from the history of the computer industry, which would be the right bet. Now, these histories work out in complicated ways. So for example, another bet that we've lived a bunch of times is special purpose versus general purpose hardware. Back in 1988 and so on, when we first released Mathematica and so on, people were always coming to us and saying, oh, we have this computer with a very long instruction word. We have this computer that does special kinds of arithmetic. We have this computer that has the special array hardware, et cetera, et cetera, et cetera. Won't you support that stuff? And we typically say, if you'll pay us, we'll support it. And or sometimes we'd say, even if you pay us, we won't support it. Because what was happening was these things like the floating point unit used to be a separate processor, and you could buy a Mac with a floating point unit or without a floating point unit. It was a separate thing back in 1988 and so on. And then the question was, would one sort of build things that were sort of specialized to the particular kind of hardware for one computer or not? Or would it be the case that in a few years, that was all a waste of time, because in a few years, that special purpose hardware would have migrated to be part of the general microprocessor, and then supported by language compilers and all that kind of thing, so that it was a total waste of time to have independently supported that that piece of special purpose hardware. And so this repeated itself, I don't know, 10 times of the special purpose hardware. People were like, look, it's amazing, it's special, it's you know, it's going to make something go even faster and so on. But then it would get, you know, submerged into the general purpose hardware. And I have to say, one place was, so that was the general historical trend. One place where that didn't happen was with GPUs, where I thought that was going to happen and it didn't happen, and it still hasn't happened. It's an interesting thing when people make sort of special purpose hardware for neural networks. Is that something where it's fundamentally going to be another piece of hardware? Is it going to be part of the microprocessor, and it's going to be something that's supported in the generic languages? Is it going to be separate kind of separate system calls, separate language constructs, and so on, or not? These are things that sort of the lessons of history tell one some things about what one should expect there. But sometimes the lessons of history doesn't always quite repeat itself. And but it's sort of been an interesting thing that the whole question of will the emulator actually work is like, you know, back in the early 90s, people were talking about this, and it's like, it's not going to actually work. You know, people would try and emulate this with that, and it's like, no, it's just not realistic. And I think I don't know why emulators started working at some point. I think it was partly perhaps that some aspects of operating systems, people agreed to license features of that software or layers that allowed system calls to work properly. I'm not sure if that was the thing, because otherwise you have to emulate the system calls as well as emulating the raw hardware, and you have to emulate kind of all the ways in which things interact with like device drivers and so on, which gets you deep into the sort of hardware of the computer, beyond just saying, oh, we get these standard, you know, instructions that you could get by compiling a C program to run. All right, I better wrap up there. Thank you very much for joining me. And I see there are all sorts of interesting questions here that I did not get to, and I look forward to getting to them another time. Thanks, and bye for now.